Everybody, since this is a video, you don't know how many people are standing in front of me. I can tell you there's very many. Today I'm going to wrap up the course. It's the semester's last course. I will start by finishing the DHT, distributed hash table, refreshing it and explaining a really nice way to do broadcast when you have that. And a really nice application we did to show you the power of distributed Wikipedia. And then I'll talk about SuperPeer. This is peer-to-peer when the peers are heterogeneous, when they have different power, and there's different ways to take advantage of that. And one way is called gradient topology, and it's based on power laws. When you look at the power of all the peers, it has a very interesting distribution, and Skype used to be using this, so I'll talk about that. And finally, I will present Raft. This is a consensus algorithm which has the best power that theoretically you can have, so up to just less than n/2 can fail, same power as Paxos, but it's easier to understand, much easier. So it's a reformulation of the very old Paxos algorithm in a more modern and easy to understand way. Okay. So, we start. First, a couple of seconds respect for the Ukrainians who are still fighting for their freedom and for our freedom. Okay. Let me first summarize, refresh your memory on, let me go to the right slide, on DHT, on distributed hash tables. So a distributed hash table is a way of connecting a bunch of nodes together so that it's self-organized. You can store information, so it's kind of a database. It's like a key value store. And the idea, the trick that makes it work is that the nodes, the computers, and the files, both of them have keys that live in the same space. So you can put the files close to the key of the node. And that's how you store them. So that's the idea. And then distributed hash table. So it's basically a hash table, like, you know, mapping between some keys and some values, but it's not stored in memory. It's stored over a whole network, mapped over a whole bunch of nodes, according to the key and this key identifier space. So the different entries are mapped to different places, and these values can be very big. They're usually very big things, like huge, like movies or something. And these nodes have routing tables, okay? And the basic operation is look up. You can also update, and you can route from any node. So that's the idea. Okay, let me now explain to you. So there's different ways of doing this. Let me refresh your memory on a very general approach called DKS, distributed k-area search. The key space, we make it into a ring. Here we have, just as an example, we have 4 bits, goes from 0 to 15. But in the real ones, it's like 128 bits, and it's very sparse. And whenever we have a red ball here, we have a computer sitting there, and the empty balls here there's nothing there, okay? And each node has routing tables, different levels of routing tables. The top level one, so it's a binary, here it's a 4-area tree. The top level one is purple, and it goes to different quarters. Intervals, you start with the whole ring, and then you divide it, and you're basically converging. And the second level goes here to the first quarter, okay? So each node has the 2 levels, so each node has all the routing tables. Here it's only showing node 1. Okay, so routing then goes by first following the far links, the top level, and then going the smaller links. Okay? And the number of levels is the logarithm base 4 of the total number of nodes, because here we have k is equal to 4. There's, in the other system we showed last week called chord, k is equal to 2. So that each routing table only has one link, actually. Notice when k is equal to 4, you have 3 links, because the 4th link stays at the same node, so you don't need to do anything. So you have at each level 3 links when you have k equals 4. When k equals 2, you only have 1 link at each level. So I just want to show this very quickly. If you look at chord is a binary. So k is equal to 2. So each of these is actually a different level, Should be different colors, The top level, the second, the third, and the 4th level, Okay? Whereas, so k is equal to 2. Whereas you can actually do more general. So here we have k is equal to 4, but k can be any number, and you choose k to kind of do a trade-off between the number of hops and the difficulty of managing the routing tables. Okay, so that's DKS. Now DKS has some very nice principles to make it work. The idea is that when there's failures, the system will repair itself, it will fix itself automatically. So it's like a living organism, kind of, in a way. And the way it does that, and it always has a logarithmic writing to DKS, when new nodes join and leave, it's always atomic. So there's a special protocol. When many nodes can be joining, but also nodes can leave, they can also crash, which is an unexpected leave. And the crash will actually cause errors. And the joins and leaves also will cause mistakes, errors in the routing tables. And these mistakes have to be fixed. And there's 2 ways to fix them. One of them is you fix it while you're using the system. So the lookup operation, if it notices a mistake while it's routing, it will fix it. So the more you use it, the more you fix. There's another technique called periodic stabilization. This, if you don't use the system, you have to do that. If you don't use it, it's just sitting there, then everything will just be degrading all the time. So you have to fix it too. So you have the second technique, which it's not mentioned here, because it's a more standard. This is a more innovative technique. Periodic stabilization, where periodically you will follow all the routing table pointers, and if there's a mistake, you fix it. So that's causing overhead, whereas this one does not have any extra overhead. And there's another one for fault tolerance. The data is replicated, but I'm not going to explain that here. So the data also is replicated. Okay. Let me just give you one example of correction on use. So I want to look up from node 1, I want to look up the key 13, but it's here. But new node 14 has joined. That means this pointer, which is pointing to 15, that's wrong. It's a mistake because you have this new node 14. Okay? So when you route to there, you will route to 15, because node 1 does not know that 14 has joined, so it routes to 15. But 15 knows that it's a mistake. 15 knows that there's a new node 14, so it sends a message saying, I'm not the responsible one anymore, it's actually 14, and not. For the key 13, there's always one responsible node, so it used to be 15, but now that 14 has arrived, it's 14. So he sends a message back saying, that's a bad pointer, the better one is 14. Okay? So then the node 1 can will fix its routing table and route to 14. Okay? Like that. And then it will be, this routing table will be fixed. Now this is a candidate Because maybe more nodes are coming in. See, this is very concurrent. 14 might not be the real responsible. Maybe there's another node coming in here, or another one even. So, but 14 is closer. So it's always converging, okay? So that's a correction on use, okay? And that works pretty well. If you do lots of lookups, the more lookups you do, the better it goes. Here's the average lookup length. So you see, if you don't do so many lookups, it's slow, because the routing tables have mistakes. See, here we have made 10% changes, so there's lots of mistakes in the routing tables. But the more lookups you do, the more the routing tables get fixed, and eventually it converges to the correct one. The two lines are for k is equal to 2 and k is equal to 4. So k is equal to 2 is the first system we saw, it's chord, and k is equal to 4 is the DKS example. So you can see k is equal to 4 has less hops. The price is bigger routing tables and more work to fix them. Okay, so that's DKS. Okay, so that gives you a refresher. Now I want to show you something really neat. You can use this structure to do very nice broadcast. So assume you have this system, you have underneath you, you have this DKS and it's fixing itself, it's always converging, it's nicely managed. You can use that to do broadcast very easily. So this was actually a publication we did in a project. Okay. So a DHT, so why do you want to do broadcast? Well, a DHT is like a database. But maybe you want to have complicated queries. Maybe you want to say, I want to look up all files such that the file name has this word in it. So that means you have to do queries on many nodes. Arbitrary queries. That means when you do the query, you have to send it to many nodes. So that's why you need to do a broadcast. Okay? So the problem is, I have a DHT, a very nice one. It's managing itself. It's very, very good. It's converging. It's like a living organism. It's always fixing itself. I want to use this to do broadcast. Efficient algorithm for broadcast. And what's very nice is that algorithm does not depend on global knowledge. You know, this whole system is every node has its own little routing table and it's fixing it, but it doesn't know everything, okay? You can have 100,000 nodes, and the whole system is maintaining this nice structure. Okay, so how do you do broadcast? Well, we're going to build a spanning tree dynamically on top of the routing tables, distributed k-array search. So technically, this is equivalent to best effort broadcast because it depends on the initial node being correct. So the one doing the send has to stay correct during the broadcast. Okay? If you want to do something like reliable broadcast, you can do that too, but then you have your algorithm is a little bit different. Okay? So remember the DKS, the DHT as a DKS, it's like a tree, okay? Where the top, you start from some node, so the ring is going left and right, huh? And each step down, I break up the ring into pieces. So here I have one piece and another piece. Here I have 1, 2, 3, 4 pieces. In this example, k is equal to 2, okay? Now, each interval has one node which is the responsible node, which is the one that you send something to when you want to go to that interval, okay? So that's the R. And S is the original one that looks up. So basically, when I do a lookup, let's say I want to send a message to all nodes, I basically have to follow all these links, okay? You see, that's kind of the easy way to do broadcast, is at each level, I follow all the links. And then all the nodes get it, right? But the problem is, there's usually much fewer nodes. Many of these links are going to the same node, okay? So if you do that, it's kind of wasteful. So what you want to do is you want to kind of optimize it. Okay. Okay, there's other ways to do broadcast, of course. Remember Nutella, which is random peer-to-peer. That one, you just do kind of flooding, okay? But, so it's very inefficient. So the con is it's inefficient. The pro is that it does pretty well as a broadcast. Or in DHTs, okay, if you traverse the ring, remember the ring has predecessor, successor, then it's good, no redundant messages. It's efficient in number of messages, but it's sequential, so you don't want to do that. Okay? It's also sensitive to failure. So we want an efficient algorithm, which is also a fast algorithm, which is doing a small number of messages. Okay. So what you do is you see you have this tree. Every node has the routing links going to the next level, but there's lots of overlap because it's very sparse. Many of those routing links go to the same place. So what you do is you actually are going to chop up the tree with forwarding limits. I'll show how that works so that each node receives the message exactly once, and not many times, and with disjoint intervals. So that's the best way to show it is to show an example. So let's say I have chord here, and so I have these 4 links, the top level, the second, third, and fourth, and the dark balls are where there's computers, okay? Notice that 2 and 3 are both pointing to that computer. 5 is actually pointing to number 6, okay? And so I want to do a broadcast starting from 1. So I send to all of them. First of all, here I have 2 3s. These 2 links are both pointing to 3, so I only have to send to 1, so I don't send to the other one. But then these, I send 1 here, 1 here, 1 here. But to make sure that there's no overlap, I add a little bit of information. I send, this one sends to 3, and then it will keep on sending, yeah? But I say it only sends up to 6. That means when I send to 3, when it forwards below, it will stop here. Because, why am I doing that? Because I'm already sending a message to 6. Okay, so I'm stopping at 6. So when I send to 3, it's actually going from the interval from 3 to just less than 6. And the 6 will stop at 9, okay, limit at 9. So when I send to 6, it's going to go just less than 9, and the 9 will go all the way to 1, okay? And then, so this is the first level of the tree, and now from 3 we go further, okay? Okay, so this is the 3, yeah? The first 3 I've dropped it. So the routing table from 3 looks like this. It goes to 4, it goes to 6, it goes to 7, and it goes to 12. But the limit is 6. That means I'm not going to send to 6, 7, or 12, because it has to be less than 6. I will only send to 4. Because I don't know, I don't have to send to 6 because this one is already sending to 6. You see, I've actually put a limit here. Okay? Because someone else will be sending to 6. And it's kind of recursive. So if you keep doing that, then you get a tree that looks like this. Okay? You start by going from 1, which sends to 3, 6, 9. 3 has a limit of 6. 6 has a limit of 9, it goes only to 7. 9 has a limit of 1, it goes to 10 and 12. Okay? 10 has a limit of 12, because this one is already going to 12. And then 12 has a limit of 1. So it goes to here, so this one is going to send to 15. And that's it. So every node will receive exactly 1. And the way it's done is that you add a little bit of information whenever you send a message down, giving the limit, how far it can go on the ring, okay? Because you know you're partitioning the intervals, okay? to disjoint intervals. So that's how you can do an efficient broadcast, okay, on this. So this is taking n-1 messages. But of course, broadcast has to take n-1 messages, right? Because you're sending to n nodes, okay? So that's not really scalable, huh? But broadcast is not a scalable algorithm, so that's really not a problem, huh? So this was implemented and simulated. Here you have the number of nodes, 8, 16, all the way up to 16,000. Here it's the number of messages for a broadcast, okay? If I have 16 nodes, then the broadcast takes 15 messages. Whereas GNU-Tella flooding broadcast takes many more messages because it's very redundant. So you see it's like a difference of a factor of 4. And here it's even more. If you type 8,000 nodes, then you only have 8,000 messages in the algorithm I just showed you. But if you do a flooding, you have 100,000 messages almost, okay? So it's very efficient. You can also measure the message redundancy. That's how many extra messages there are. And the algorithm I showed you, it's 0, okay? In the algorithms, if you do the Nutella one, most of the messages are redundant. 60% of the messages are useless, are redundant messages. And if you do, for 16,000 nodes, you have more than 90% of the messages are useless, are redundant. You would only need, if you would be smart, you would only need a small piece. Because they're always sending to the same node over and over again. Okay? So you can see the structure of the DHT gives you efficiency, whereas a random network doesn't do it. Okay? Okay, let me just tell you one more thing about DHT. So a DHT is like a framework. You can actually use it as a platform and build applications on top. So I'm going to show you an example of that. You can use a DHT. So let's say I have a running DHT on many nodes. I can build application on top as an infrastructure because it gives me lots of basic services, the DHT. It gives me storage, replication. It can give me transactions, which I didn't show you, but it can do that. It gives me broadcast. So you can build a scalable application on top of it. And in a project, so we did this actually, so this is something we have experience with. We built a DHT called Scalars, and we built an actual replica distributed Wikipedia, large scale, running on hundreds of nodes. This one actually won a prize, okay, Scalability Prize in 2008. So this is actually practical. And the way it's done is that you have lots of components, small pieces that are sitting in the DHT and on top of the DHT, okay? We also did another application, which I won't talk about, but it's in the slides, collaborative drawing application. If you have multiple people working on the same drawing, very complicated drawing, then the storage is managed underneath by the DHT, okay? Okay, so here's a DHT, but here it's like a black box. But actually there's lots of stuff inside there, okay? I showed you some of it. Of course, there's the network. There's a failure detector in there, of course, because how else would you know that the node has failed? There is the ring, the predecessor successor node. There is periodic stabilization, which fixes routing tables, like I said. There is a router. There is topology maintenance, so basically fixing routing table general. There is also merge ring unification. What if you have partitioning of the network and then the partition goes away? So this thing really fixes itself. So you see there's already all kinds of stuff in there. So we added more stuff So we added, so at the end, there was all this stuff sitting in the DHT. Okay, you can see there's the failure detector. Here's the structured overnight network. We built a transaction algorithm in there. We built a Paxos consensus algorithm in there. We built replication in there. Multicast, so more general broadcast in there. Okay, we built a cache in there. We built broadcast gradient, which I'll talk about. Aggregation, which is like doing computation on all the nodes. Remember we did aggregation in the Gus. So in the project Selfman, we added stuff into the DHT to turn it into a really useful kind of application platform. Okay? And we built two systems, Scalars and BeerNet. But I will talk to you mostly about Scalars. So this was a real thing. This was a key value store that we developed in a project called Selfman. They provide transactions, something I didn't show you yet. You can do transactions using Paxos for the consensus, for the commit. And we built them up to hundreds of nodes. And Scalars actually won a prize, and I want to say something about that. Okay? So the thing has three layers. There's the overlay. This is what we just saw. This is the routing tables. But then there's data replication. Each data is replicated in multiple places. And if maybe 4 places, each file exists in 4 copies. And if one of the copies fails, then there's only 3 copies. And the system detects that, and it creates a new 4th copy. It finds another node, because there always have to be 4 copies. So you see, if you have like 4-fold replication, and the thing is always degrading. Remember, we're living in the world where there's always nodes failing and so on. If the number of copies is less than 4, the replication will detect that and will select another node that takes the place of the crash node and copy a replica on that. So that there's always going to be 4, or if there's not 4, it's converging to 4. Okay? Of course, if all 4 of those nodes with copies all crash at the exact same time, then the data disappears. Okay? But normally the chance of that is very small, because these 4 nodes are very separate, widely separated. Okay? Okay, so let me show you how the Wikipedia works. This is another application called dtransdraw, which I'm not going to talk about. It's a distributed drawing application. But let me talk to you about the distributed Wikipedia, because this one was really working at a large scale, and we made a copy of Wikipedia on it. So let me explain to you first something about Wikipedia. So this is in 2008. In those days, very long ago, the top 10 websites were these. You can see many of them are still known nowadays. Yahoo, Google, YouTube, Windows Live, Facebook was already there, MSN. MySpace has disappeared. Wikipedia was in the top 10 websites of the whole web. And the Wikipedia system was taking 50,000 requests per second. That's pretty big, huh? 50,000. So if you, over the whole world, in 2008, the Wikipedia system accepting 50,000 per second. So how is this organized? Well, there's a front end, which is basically having copies of the data. These are called proxies. There's a certain kind of proxy called a squid proxy. This is kind of like a company that exists. You can have these proxies. So 95% of these queries are handled by the proxies. Okay? And then you have the back end, the actual database, which is sitting behind the proxies. This is what happens when you actually update the Wikipedia. So only 2,000, which is divided by 25 of these requests are actually hitting the backend. But still, the backend has to accept 2,000 requests per second. Okay, and here this is like calendar. Here you can see how it varies depending on the day and the night. okay? And you see different kinds of data, images. So I'm not sure exactly what these categories are. Images, KNAMs, I'm not sure what that is. But there's different parts, so you can see how it fluctuates, the green and the purple ones, over the day and the night. So here's a picture of the Wikipedia architecture, kind of a picture. These red cones are the proxies. So here's the open internet making requests, okay? Here, the green ones is the actual database. This is a MySQL database with many nodes, okay? Then you have other kinds of things. You have the web servers for making for creating websites. You have search servers and other kinds of things doing certain kinds of controlling and management stuff, okay? So you can see you mainly have the proxies here and this MySQL database, okay? And just to give an idea how it's working, the data model, let me just give you a quick explanation of the data model. So this is the actual Wikipedia. So we made a copy, we made kind of a smaller version of it on Scalars. So Wikipedia is using an SQL database, which you maybe know on a SQL, which allows certain kind of queries, relational database. We mapped that onto a key value store. So you have tables, okay, which I'm not going to say much about, but you have many tables in the Wikipedia, and we map this to pairs, key values. So, for example, for a particular title of a page, you have versions. So you would have a key value pair, which is the title and the list of versions. And then you have categories. So Wikipedia has information structured in categories. For each category, you have a list of titles. Okay. You also have backlinks, okay, where pages can point to other pages, so which also a list of titles. So all of this is key value. So you're mapping this whole Wikipedia structure onto key value store, okay? And then you have just an example. Let's say I want to update a page. I have the title, I have an old version number, and I have the new text. So I'm going to create a transaction. So this is kind of the pseudocode, how it would work. I create a new transaction. So this is all done in a transaction. I read the title, okay? If the current version is not the same as that version that I'm doing, then I abort. Then it's not good. It has to be the same version. Then I will write the new text. I will update the categories for each category C and P, and then I commit. Okay, so I'm just doing regular old transactional stuff on top of Scalars. Okay, so it's very, very classical. Okay, so Scalars looks like this. Scalars is very similar to what we saw. It is very similar to Chord. It has some variation. It's called Chord Sharp. And then there's an input, a load balancer. So when clients connect to this, because you have many nodes here, the load balancer will somehow distribute the work so it doesn't get concentrated on one particular node. Okay? So you have web servers here, and you have replicas of the pages, and it's all around that thing. Okay? So there's hundreds of nodes in that. And then there's things like rendering, interface to airline. There's a whole bunch of utilities. So this is what the Wikipedia looks like. This is a page generated by the Scalars Wikipedia. Try reading that. What language is it? It's kind of weird, huh? It's actually Bavarian dialect. What they did was they wanted it's smaller than the English Wikipedia. They took a copy of the Bavarian, since these guys are in Berlin, they're German, this group in the the Zuse Institute. So they actually made a copy of the Bavarian language Wikipedia. It's funny, huh? So that's what it looks like. But otherwise, it's still pretty big, actually. Okay, and then this was in the IEEE Scale Challenge. So this was submitted to an IEEE contest for the most scalable application. Okay, so this was a distributed application. All these Scalars was running on very many nodes. See, it was the Bavarian one. There's also the Simple English. There's a Simple English Wikipedia. You know, there's a version of English called Simple English, which has only the simple words for non-English speakers. So they did that one too. And it's actually a pretty good functional one. So they deployed two versions. One of them was deployed on Planet Lab. So Planet Lab was like a worldwide network where universities keep their nodes and they're all connected together and you can run applications on it. But it doesn't work so well because many researchers use this, so it's always overloaded, okay? So they had a 20-node version of that. But they had in Berlin, so this is where the lab was, they had large, this is the supercomputing center, so they have large clusters. And so it was running on 320 high-performance nodes. So that's pretty much, that's a big distributed application. Huh? So this thing won a prize, and they got a plaque, an engraved plaque, and this is it. Okay. Wikipedia on a DHT. So here the guys that did it. This was in a project that we did called Self-Man, which I was part of, was coordinating, so I was very happy. This is the International Scalable Computing Challenge, International Symposium on Cluster Computing and the Grid in 2008, the IEEE Technical Committee on Scalable Computing. So they won that year's prize on scalable computing. Not bad, huh? So we were all very happy on that. So it shows you can really build true, real applications on this, okay? Okay, so conclusion, DHT is actually a practical system to build scalable, decentralized applications that are efficient. Okay? You can use gossip, but it's not efficient. You can have services, and we showed that with Scalars and Gearnet, and we built several applications, okay? So the distributed Wikipedia won the prize. So there. So I had to show that. Huh? Okay, so now that's all I want to say about DHT. So you understand how this works, huh? How you can build a large, self-organizing, efficient system, the principles of how it works. Now I want to show you one more topic related to peer-to-peer. So this is a peer-to-peer. DHT is a decentralized system. There's no server node here, but it has structure. And I want to show you now another kind of peer-to-peer, which is different from DHT. It also has structure, but it's kind of closer to gossip, okay? The structure is very different. So let me show you that one, called SuperPeer. Okay, let me show you this one. Okay, what I want to show you now I want to show you another kind of peer-to-peer algorithm called SuperPeer. But let me, in order to set the stage for that, let me make a picture which kind of organizes the whole thing. So here I have large-scale distributed system, okay? So we saw different kinds of that, okay? We saw gossip. This is like the root, huh? This is working on a random network. This one is the most robust. It basically can work on extremely hostile networks. Now we saw different ways of extending it. We saw BitTorrent, which is an example of content distribution network. And the difference is that now we have selfish nodes. So BitTorrent is also a kind of gossip. Huh? Each peer knows random peers. But what's the difference? Well, here you have selfish nodes. So you have to use economics, where you have the choking and the unchoking, where I reward you if you reward me. So the nodes have to kind of work together. You have selfish nodes. So it's in the gossip here you don't. Here all the nodes are just doing the algorithm. The second one, which I'll explain in a minute, is called SuperPeer. Here, the thing is you have heterogeneous nodes. That means nodes that are very different in power. You have some nodes which are really strong, big computers, others which are very small, like maybe mobile phones. How do you organize that? So that's what I want to talk about there. And the final one that we saw was DHT. Both of these two are kind of still random. In the DHT you add order. It's more ordered. So it's more efficient, but less robust. Okay, there's this trade-off. Gossip is extremely robust, but it can be slow, whereas the DHT, as you saw, can be very fast. You can do transactions, you can use it like a real database, and it repairs itself and everything. But it's not quite as robust as gossip. Now, you can actually combine these two. You can actually combine gossip and peer-to-peer to get what's called hybrid gossip, which somehow takes the sweet spot of both. So basically it uses the DHT, but if the DHT breaks, it uses the gossip to fix it. Okay? So it's kind of a very nice sweet spot. This one is actually used in real systems on cloud. There's an algorithm that is called Plum Tree, which uses both of these two ideas. Okay, so that's kind of the thing we saw. You can also extend these. You can add order to these. Again, to make it more efficient. More efficient, but also more fragile. So you can, there's many kinds of variations you can do. And in the real world, you'll see all kinds of mixtures of this. Okay. So that gives you the whole big picture. So what I want to do now is show you the SuperPeer. So this is what you do if some of the peers are really strong and many of them are weak. You don't want to put them all in the same level. You don't want to put them all as nodes in the DHT because the weak ones are going to be failing all the time. So what you want to do is take advantage of the strong ones. Okay? So that's what SuperPeer architectures do. Okay? And Skype, the version of, at least several years ago, now I don't know anymore because nobody really knows except for Microsoft what's inside of Skype. But several years ago, Skype was using this idea. It was using SuperPeer when it was first became very popular. So we take peers with better characteristics to somehow help the other peers. You have the strong guys carrying the heavy stuff, and then the weaker guys are just like users, clients. Okay. Okay. Maybe it's 5:10. Maybe I make a few minutes of break now, and then I'll explain that. Now I want to talk to you about SuperPeer architectures, where the peers are heterogeneous, and you want to take advantage of the strong peers. So let me go over, these slides are what we saw before. Let me quickly skip them. all peers are not equal. Peers are heterogeneous, that means they're very different. Some of them have big bandwidth, some of them are up more often, some of them have an open IP address, they're not behind a NAT network address translator, some have low latency, some have more powerful. You see there's a lot of ways that the peer can be stronger. Huh? And there's some statistics that were done. So these are very interesting graphs, so it's important that you kind of understand what they're showing. Here we're looking at two applications, Napster and Gnutella, which are file sharing applications. And on the horizontal is the percentage of uptime. So here we have 60%, so all the nodes which are from 0 to 60% time up. And here is from 0 to 80%. So for example, if you look at, this is the percentage of hosts. So Gnutella, for example, the host, 80% of the hosts are only up 40% of the time, or less. You see, you make a little bit more than 40%. So these are cumulative functions, cumulative distribution functions. So this kind of cumulative function is used a lot. So you have to really exercise so you can read these kind of graphs. If you look at Napster, the green one, 80% of the hosts are up from 0 to 80% of the time. You can see that they're more up. So for example, 20%, between these two lines is 20% of the nodes. They're from Gnutella, they're up from 40 to 100% of the time. So a lot of them are not up so much. If you're only up 40% of the time, that means more than half the time you're down, you're out. But Napster, if you look at this band, that these 20% of the nodes are up 80% of the time. So you see that the Napster nodes are much more likely to be up. Okay? And here on the right graph, you have session duration, how long I open my session and then I close my session. So how long does that take? You can see that from 60% of the sessions are going to be less than 100 minutes, 80% are less than 200 minutes. So if you want really long sessions, like 10 hours, you only have a few percent. So most sessions, the median duration is 60 minutes, so it's right here somewhere. So it's not that long, maybe 60 minutes, 1 hour. But some of them are much longer. So these would be weak peers, but these would be strong peers. You see that? There's a difference. You have some very strong guys here, but also some weak guys here. Here also, you have some very weak guys, which are most of the time they're down, but you also have some other ones that are most of the time they're up. There may be only a few percent, but they exist. Okay? So from these graphs, you can deduce that you have a lot of variation. Okay? You have weak and strong peers. And here's another interesting graph, the latency to the peer. Okay? So this was in 2002. This number probably went down a little bit today. So here you have the millisecond latency in a logarithmic scale and percentage of hosts. So 50% of the hosts have a maximum latency of 100 milliseconds or less. Okay? But again, there's variation. You have 20% have 70 milliseconds at most. Whereas the higher 20% here have, if you look at it down there, it's actually, because it's logarithmic, it's 280. It's from here. It's here, it's 280. So from 70 to 280. So you have here some very low latency peers, okay? And here you have high latency ones. So again, you see that there's variation, okay? So that's the important thing out of these graphs. You have to read these graphs. If I ask you, for example, in this graph, how many percentage of the nodes have a latency that's less than 50 milliseconds. You should be able to, with a ruler, figure that out. So 50 milliseconds will be here somewhere. So if you go like that, it should be like around 10%. Okay. 10% of the nodes have a latency of maximum 50 milliseconds. So those nodes are very well connected, but there's only 10% of them. Okay. But they exist. And here on the right, we have also a very interesting graph. We have the bandwidth here and the latency. So those are two independent numbers. This is kilobit per second. So here you have 1 megabit, but 10 megabit, 100 megabit. And here you have the latency. So here there's a big bunch of them. So most of them are like 2 megabit with 100 millisecond. We have two lines coming out here, which is like, this one is 100, like 90 millisecond, and this one is like 200 milliseconds. So there's a whole bunch of faster ones and a whole bunch of slower ones, and even going very, very high bandwidth. So at 100 megabit, you have a significant number of peers here, okay? You also have a funny cloud here. So this is with very low bandwidth, and very low and very high latency. So these guys are not so good. The better ones are here. So you want to go down and to the right if you want good ones. Low latency and high bandwidth. See, so this is interesting to see. So this is actual measurements. So this justifies SuperPeer, because you can see there are many different kinds of peers, and some of them are strong and some are weak. So here's another one, the bandwidth to peers. So this is with file sharing applications, fast track, direct connect, so bandwidth and cumulative distribution. So you can see there's low bandwidth guys here, but there's also high bandwidth guys here. So there's 20% of them have at least 1 megabit. So this was in 2004. This measurement. So here again, this is another application similar. So again, you can see that you have slow guys, but also fast guys. So you justify the SuperPeer. Okay. So you have to read these graphs, Okay. So what is a SuperPeer? Okay, a SuperPeer, it's not just a peer, it's also a server. The SuperPeer is a node in a peer-to-peer network that is a server to a bunch of clients, which are the weaker peers, but it is an equal in a network of superpeers. So the superpeers talk to other superpeers. So you have these big gorilla peers talking to other big gorilla peers, and the little guys are using them, but the superpeer only talks to other superpeers. So they have high utility relative to non-super peers. So utility is what? It depends. Maybe they're faster. Maybe they have high bandwidth. Maybe they're not behind a net. Okay? And you can actually measure the utility, and the peers that have high utility, you promote them. Okay? You turn them into super peers dynamically. So anybody can become a super peer. Okay? So the SuperPeer network, you exploit that. You take advantage of these high utility peers to make the whole system run better. Okay? And the example I'm going to show is Skype, where in the olden days, Skype was like a parasite. It was running off of all the client nodes. So some clients were very strong clients, big computers, high bandwidth, and Skype really used those to connect people. Nowadays, it's probably using more Microsoft infrastructure, but in the olden days, it was really using SuperPeer things, okay? So it kind of looks like this. You have these big guys, these SuperPeers, and then you have these ordinary peers around it. And the SuperPeers are themselves in a peer-to-peer network. But these little peers, they're clients. So for this little peer, the SuperPeer is like a server, okay? So for the SuperPeer is strong enough that it can handle many of these little guys, okay? So you see how it works, huh? The actual peer-to-peer network is among SuperPeers, not among regular peers, okay? So there's if you want to do it, there's a kind of design. How do you want to do it? Okay, what kind of topology? So I'm going to talk some of this. How do you organize it? Is it random, like gossip? Is it DHT? And then there's a new one I want you to present. It's called gradient. So this is a very nice one. And what about promotion? How do you promote a peer? Because you're going to promote peers dynamically, yeah? So there's lots of services. File naming, retrieval, voice over IP, this is Skype, and file sharing, other things. You can do actual other kinds of applications. So the SuperPeer can actually do a lot of things. Okay, so how do you connect SuperPeers? 3 main ways. Random, okay, gossip style, flooding, gossiping. That's easy, but maybe slow. DHT, but this is not actually used. It's harder because you're promoting them dynamically. So this DHT would be have very high churn actually. And then this third one called gradient. So this is actually a very nice one. So I'm going to talk to you about gradient, which is the new thing, okay? Okay, so the way gradient works is that all the peers are kind of living in the same space, and each peer has utility. And there's kind of a gossip algorithm so that the peers will have connections to peers with the same utility. Yep?
I have a question about
sure.
The last illustration with the SuperPeer architecture. So,
this slide or previous slide?
Previous slides.
Okay.
I'm
this
not
one?
sure, but yes, to me it looks like this. It seems like it's like the edge computing architecture, but I'm not sure if it's.
That's a good question. It's like edge. Well, actually, yeah, this fits very well to edge, actually, because this is what you measure. Huh? You measure strong guys and weak guys. But if you look at edge computing, you have strong guys and weak guys. So the strong guys would be the data centers, the strongest one, and the weakest would be these little sensor nodes on the very edge. So a SuperPeer architecture is actually a good fit for edge computing. Yeah. And in fact, these guys can be actual data centers. Huh? Probably, so now I'm guessing, so Microsoft, when they bought Skype, they probably reorganized Skype. So Skype was using this kind of an architecture. So my guess is that the SuperPeers are actual Microsoft data centers, okay? And they have very huge computing power, they have very high bandwidth, and each of the clients here have very fast, low latency. So for example, so I live near Paris, and if you are 30 kilometers from Paris, the latency is like 1 or 2 milliseconds to Paris. Okay. So that's okay for Skype, huh? So this actually fits very well. So this kind of architecture is getting more popular, I guess, with edge computing. Edge computing is a thing. So we actually had some project on that. It's huge growing. Huh? It's very popular, and it's growing exponentially still. And the edge, so all these little guys together, is actually bigger than the center. And the edge is growing more than 10%, 13% per year, and the center is only growing 5% per year. So in French you would say l'écart se creuse, the difference gets bigger and bigger. Huh? So yeah, so this kind of architecture becomes more and more useful. Okay. And the way you maintain it is you use gossip. So there's a gossip algorithm, and each peer tries to become neighbors with peers of the same utility. So the strong guys will naturally kind of collect together, and they're in the center here. Huh? So at every level here, the neighbors are the ones that have similar utility. So the weak guys, the little guys, will have neighbors that are little guys, but not always. You have actually two sets, because you can't completely separate them, because the little guys have to know the strong guys. So you have two kinds of neighbors, similar neighbors and random neighbors. So the little guys will also know some strong nodes, okay? So that's a gradient where it gets stronger near the center, okay? So here is two topologies. On the left you have random, and the color is the utility. So the darkest one is high utility, the lightest one is low, is small, like ordinary peers, very low utility. In a random network, they're all kind of mixed together, and you can't really do search very well on this. What if I want to go from here to there? Well, you can't really, you go through weak nodes, it's not very efficient. But here at the right you have a gradient topology, and so all the strong guys are in the middle. And the nice thing about these strong guys is that they can keep directories. They have a lot more memory and computing power. So if I want to go from here to there, it's very easy. I climb up to the center, and then I descend on the other side. So it's you go up to the center, and then the center guy will tell you which direction you have to go, and then you go down to this one. So you can actually do routing on a gradient topology. And it works because these center guys have huge power, and so they can keep lots of information. So this black guy can keep a lot of information about who is next to him, okay? That means if I want to go from here to there, this black guy will know where this guy is, okay? So you can actually route in a gradient topology. And so you can see it's very nice. You create this using gossip. It's automatic, and it automatically maintains itself, and even better with edge computing, and you can use it for routing fairly efficiently, okay? So it actually works pretty well, okay? So that's a good thing. Okay, one more thing I want to talk about is the promotion. There's a kind of algorithm that promotes peers to become super peers. Well, actually, it maintains utility, yeah? And the top X% of the peers are somehow going to be in the middle then, huh? So you have to maintain the utility. And then there's a whole bunch of techniques. How do you promote? So going from random to SuperPeer, eventually some of these guys will be promoted and they will become super peers while it's running. Okay, so I'm not going to talk about it so much. What I do want to talk about is what ties into something we saw before, which is the small world networks. I want to talk about power laws. Okay, I want to study a little bit more, again, the heterogeneity. And how can you organize, how do you see all these different peers? Well, they're actually, remember we saw these cumulative functions, okay? But if you look at that a little more closely, you can see that the distribution is actually power law. And here's an example of how it works. So here, for example, I have cities. So here's the population of a city, 200,000, 400,000. And here's the percentage of cities. So there's a very bigger percentage of cities with small population. If the bigger the population, the less cities you get. So this does not look so useful, huh? It's supposed to zero here, huh? But if you make it into a log, it's much more useful. Because then it turns into something that is almost like a straight line. Here you have population, 10,000, 100,000, 1 million, 10 million. And here the percentage. But here it goes down, really, 10 to the minus 5, minus 6, minus 7. And if you do that, then you really get a good way of looking at the real big and the real small cities, okay? It's a power law. The power law says that the probability that the number of the population is bigger than or equal to x is proportional x to the minus alpha. This is a power, and that's why it's called a power law. But if you take the logarithm of this, it turns into a straight line. And here you have the logarithm of the probability. Here you have logarithm x. You can see it's linear. So a power law exactly turns into a straight line. And that makes it really nice. And then we can study the peers like this, okay? And another property of power laws is scale invariance. That means it looks the same whether we magnify it or not. What does that mean, it looks the same? Well, if we magnify the scale, if we multiply this x by some number, we change the scale, then this x, if we say beta times x, he will have beta to the minus alpha times x minus alpha. So this also is multiplied by constant. So the probability is also changed by constant. So if you change your scale of x, you're changing also your scale of probability. But it's still a straight line, okay? So what that means, what we say, it's called scale invariance. It's the same exponent. The exponent stays the same, no matter what the scale is, okay? Okay, and here's an example of a power law. So this is a very nice one. This is called Zipf's law. So Zipf was a linguist, and he looked at words in a language, and the words, which is the most popular word, okay? Of an event to the. So in English, for example, the word the is very popular. And if you rank the words, the most popular, the second, the third one, the fourth one, then the rank is R, okay? So it's a number. We have the 10th most popular, the 100th most popular. Well, again, the expected value or the probability is a power of the rank. So Zipf's law is also an example of a power law, okay? And here's even another one. You see power laws are everywhere, huh? There's a famous economist called Pareto. In 1897, he was studying income distribution. How many people in northern Italy have income greater than X? So how many they earn? I guess they had lira, more than 10,000 lira per year or something, or 5,000. And if you look at that, again, it's a power law. That means there's a lot of poor people, but there's less and less rich people, okay? So again, it's a power law. Pareto, we'll also see him in other places, huh? He has also something called Pareto optimality, which is also very important to understand how something can benefit all of society. So we'll see that also in another course, the 11-15 course. But this is also an example of power laws. So you can see lots of real-world things are power laws, okay? So that's a very general thing. But it also works for internet stuff, okay? Okay, so here's an example. Fast Track, which is a file sharing application. So here we have the rank, but this is actually the logarithm of the rank, okay? So 100, 10,000, and so on. And here is the traffic. So you rank the IP addresses according to how much traffic they have, and it turns into, it's not exactly a line, okay? But it's kind of like a line. If it's not exactly a line, but it's close to a line, it's not exactly a power law, we say it's heavy-tailed, okay? And the reasoning is a power law actually goes down very slowly. So the tail, which is the end part, stays pretty high. It's much bigger than an exponential. So e to the minus x goes to 0 very fast. Whereas x to the minus 2 is much, much bigger. Huh? So let me make it. So if you have an exponential function, it goes to 0 very quickly. But if you have a power law, it actually stays big for a long time. And if you have something which is like a power law, some other function that goes down and stays pretty big, but it's not exponential, this is called heavy-tailed. Because the tail is heavy, okay? It's the intuition. Here the tail is very light. Exponential goes down to 0. So it turns out power law is kind of the most common heavy tail. But here you have other kinds of things which are not exactly power law, but they're also heavy tail, okay? That means that these high rank, there's lots of these high rank guys, okay, in the heavy tail. So here's BitTorrent, okay? Here is you're looking at the peers in BitTorrent. Here is the uptime, how long it stays up. 1 hour, 10 hour, 100 hour, 1,000 hour, but here, 1/10 of an hour, 6 minutes. Here's the ranking. So the number 1 guy who stays up the longest is way up here somewhere. The number 10 guy is staying up like a little bit more than 1,000 hours. It's long, huh? But the number 100 guy is actually staying up less. So here we have a log thing. Notice that this is very similar kind of to straight line up to here, huh? And then it goes down faster. But up to this point, for a long, big range here, it's like a straight line. That means, what that means is that there's a lot of guys on both sides here. There's a lot of peers with very high uptime, but there's also a lot with very low uptime, okay? So that's something that's interesting to know. So here's a similar one. This is the download speed, okay? The number of download bandwidth here, and the number of downloaders. You can see it's also kind of a straight line, huh? So the download speed is also kind of a power law, okay? Okay, so that's interesting because SuperPeer algorithms really depend on heterogeneity, and you can study it and you can see the heterogeneity is very wide, and it obeys very similar to power law, and I had to show you that a power law is actually much more bigger thing than just peer-to-peer. Power laws are actually all over the place, okay? So, and if you follow the course Info 1115, we'll see, for example, power laws will also determine web page popularity. How many web pages are popular, okay? So power laws are basically everywhere, okay? Okay, then SuperPeer promotion. I'm not going to talk so much about the promotion. Let me just say a little bit about Skype. So this is Skype before that Microsoft bought them. It's a telephony system, and it's based on SuperPeer. Okay, and the reason why we can see that now is because it didn't have its own infrastructure. It was kind of piggybacking on the clients. So if I was talking to somebody on Skype, okay, then that message, that video, or that audio went through a bunch of nodes, but maybe it was going through nodes that were not talking. It had to route them. So your computer was actually helping other people, okay, if it was strong enough. It was a SuperPeer, okay. But this was proprietary. So there's a study, some guy made a study, okay, on an analysis of Skype peer-to-peer, okay. So how does it work? So we know a little bit how do you log in? You have bootstrap server, so you have connect. This is kind of like in BitTorrent, where you have these, what are they called? Starts with a T. You have these guys who would let you go into it, okay? Trackers, yes, thank you. Very good. And so when you get in, and once you get into it, so they have algorithms, so I'm not going to explain too much, for managing network address translators, NATs, because that's a problem. This algorithm called STUN. But how do they discover each other? Well, here's something very interesting about Skype. It has something called global index. But what is a global index? It's like a telephone directory, okay? If I want to talk to somebody on Skype, I have their Skype name, and I can just connect to them. But how does it know where they are? Because there's maybe millions of users. Well, the global index technology is a multi-tiered network where supernodes communicate in such a way that every node in the network has full knowledge of all available users and resources with minimal latency. This is the marketing definition of global index. We don't know anything more about it, but it seems to be a SuperPeer network. Okay? So you have a bunch of SuperPeers that are connected, making this thing called the global index. And they somehow keep track of all the users. Okay? And how does it work? Well, I'm not an employee of the Skype people, so I don't know. Only speculative information. Is it a DHT? Is it something like DNS? Is it a gradient protocol? Who knows? Is it centralized? It's probably some kind of a SuperPeer thing. Okay. Okay, and then there's some discussion about NAT traversal, which I won't talk about. Because time is running out. Let me just quickly present Raft now. So we have a few more minutes. So Raft is consensus. Remember we talked about consensus. So now we're going back to small systems with fixed number of nodes. We go away from the large systems. We have a database with 5 replicas, and they have to stay consistent. So we have a small fixed number of nodes. So we use consensus, and the Paxos algorithm is able to achieve consensus with up to just under n over 2 nodes that fail. But I did not really explain it to you because it's a very complicated algorithm. It was invented more than 30 years ago by Leslie Lamport. But my decision is I will not explain Paxos. You can read Paxos if you want, because we have something better today, which is Raft. Raft is an algorithm that's as powerful as Paxos, but it's much easier to understand and implement. And almost all systems today that need consensus are using Raft. Okay. So here is a Raft talk. So we want availability or consistency. We have a distributed system. And we don't want a single point of failure. So we want replica. But they have to be consistent with each other. How do you do that? There's 2 ways. So this is the article, the talk where they presented Raft. In industry, there is 2 ways to do that. There is what's called a hack, or in technical terms, an ad hoc algorithm. And this case is rare and typically occurs as a result of a network partition with replication lag. It means that it's buggy. Or the right way is consensus. Okay. Paxos or Raft and a consensus service, unlike Zookeeper service, for example. So consensus is kind of the right way of doing that. So what is consensus? You know what consensus is. We saw it. But they say this is their way of explaining it. You have agreement on shared state. If you have a minority of the servers that fail, it's okay. If the majority fails, then you cannot do queries anymore. The consensus doesn't work, but the system is still consistent. the data will not be corrupted. Okay, so that's useful. Okay, so consensus is very important. We want consistent storage. You need all kinds of consistency issues. So I won't get into that. You need consensus and for transactions. And here, this is a slide I showed before. This is how large distributed applications are made, like Amazon. There are variations on this idea. Okay, these are the servers, very powerful machines, and they're connected together. Each server runs code, which is called the state machine, and it has local variables. And each server also has a log, which is a stable storage, keeping track of what it did. And they're supposed to always be the same, executing the same commands in the same order. Okay? But one of them can execute a command, and then the result can be sent to the others. So you have a consensus module, a piece of code on every server, to guarantee that they're all synchronized with each other. Okay? So the consensus will guarantee that the logs are correctly replicated. The important thing is the log. If the server crashes and reboots, all the information comes to the log. So the logs have to be consistent with each other. And as long as a majority of servers are up, the system makes progress. This is our consensus. And this is running using fail stop. Because it's on a data center, these are trusted nodes. You control them completely. And you have many, many clients connecting to these guys. Okay? And these can be connected in many ways. Amazon, they're connected in kind of a very specialized, kind of a DHT-like way. You can have dozens of these guys connected together. So that's how a big application works. But you need consensus for that. So how do you do consensus? Well, the main discovery was Paxos, which was invented by Leslie Lamport in 1989, but it's very complicated, actually. So I'm not going to explain it. That's normal. The first time something is invented, it's usually complicated. So Raft is a version that is much easier to understand, an understandable one. So I'm going to give you the intuition. So it's a totally different decomposition than Paxos. And there's less mechanism, it's much easier to understand. Okay? But it's just as powerful. And they made, the inventors of Raft made a study where they taught a course where they taught people Raft first and then Paxos, and Paxos first and then Raft. And the red crosses are when they learn Raft first, and you can see that the Raft grade is higher if they taught Raft first, because if you teach them Paxos first, they kind of get confused, and so on and so on. And here you can see the blue ones is saying that Raft is easier, the red ones is saying Paxos is easier. So you see, Raft was considered much easier. But so what is Raft? So let's explain Raft now. Raft is based on leader election. You have n servers connected together, and you will elect a leader. And that one controls, the leader controls everything. But when the leader crashes, you will elect another leader. So there's basically, a leader will run as long as it goes until it crashes, and then another leader is elected. This is connected to log replication, so the leader will manage the stuff going into the log, okay? And the thing is safe, the data is consistent, because you will only elect leaders who have the good, safe information. Okay. So I have n servers, and they're in 3 states. They're either followers, candidates, or leaders. Starts out they're all followers, but if you want to run the system, somebody has to be leader. So one of the nodes says, I'm a candidate. So they start out all being followers. One of the nodes says, after some random time, I'm a candidate, please vote for me. And it does leader election, and if it gets votes from the majority, it's the leader. And so there's only one leader because only one can get votes from the majority, okay? So the system runs like this, and this is time. It runs in terms. A term is a time period when you have the same leader. So the blue period is an election. I elect a leader, and the green is this leader is running the system. Until the leader crashes, and then you elect another leader, and the system runs until the leader crashes. This one crashes right away, but this one you elect the leader, runs for a long time. Okay? So it's always either electing a leader or it's doing consensus with the leader. Okay? So that's how it works. And I'll show you how does the leader election work. So assume the leader crashes. Okay? So the leader sent heartbeats to tell the others I'm not crashed. But if it crashes, no more heartbeats. So all the followers say, hey, where the boss has disappeared, Mussolini is dead or something, huh? So a new leader is elected. How do they do that? Well, after some random time, one of the nodes will say, I'm a candidate, and it will send messages to everybody else saying, vote for me. Okay? And then there's some possibilities. Either it gets a vote from majority, and it's good, it's a leader. Okay? Or maybe it was too late, and some other guy managed to get the votes before me. Okay, that's fine. I will be follower of that guy. Or maybe there's like a stalemate. They each get exactly half, or there's nobody wins the election, nobody gets majority. Well, then you time out again. And you keep doing that until you have a leader elected. Okay? So you see it's kind of a funny random way of using randomness, huh? So if I have 5 nodes, and they're all followers, how do I elect a leader? Well, each one will run a random number generator for a certain number of milliseconds, will wait, and then it will make candidate. So basically the one that does it first will have the highest chance of getting it, huh? So how do you manage that? Well, there's actually a kind of trade-off. So here you see you have an interval between 150 and 200 milliseconds. You say, I will take a random timeout between 150 and 200, or between 150 and 300. And you see, if this interval is bigger, then the chance of a conflict is lower, okay? Because it's more space here. So the lowest one is going to win. But it's going to be slower because the big value is because it's bigger. Whereas if the interval is smaller, the election will go faster, but there's more chance of a conflict. So it's kind of a trade-off. So here the red one is a very small interval, and you can see it takes a long time. This is how long it takes. Time without leader, very long, 10 seconds. Because it's almost always conflict. Whereas if you make the interval a little bigger, then one of them is going to win more often. So there's kind of an optimal here. So the light blue, this light blue seems to be the best interval, okay? Whereas if you make it even bigger, it will slow down again just because it's a very big interval, okay? So there's kind of an optimal, and then you elect, okay? Okay, let me now show you a scenario. So this is another thing, and then we're done for the year. So this is a very interesting set of slides, which is also in the Moodle, because it kind of gives an animation of Raft. So you see how it works. Okay, I will not go here. A short history of distributed consensus. So this is very funny, right? That's the history, okay. Paxos in a nutshell. This is a really weird nutshell. Proposer, acceptor, learner, leader. It's actually very complicated, so I forget that. These are the inventors of Paxos, of a Raft, Diego Ongaro and John Osterhout. Okay. Many implementations. Okay, now I'll show you the algorithm. There's the leader. So here's a leader. Okay, you will recognize Mussolini. There's a follower. You will recognize one of the peasants from Monty Python and the Holy Grail. And here's the candidates, the guy who wants to be the leader. So here's an example. I have 3 followers. So the system starts up. After a random time, this one makes, I'm candidate, please vote for me. Vote for me, yes. And he's the leader, and that's very nice. And then the leader manages everything. He manages the log entries, okay? And everything is fine. And he sends heartbeats. Oh, the leader crashed, very bad. That's not a problem. This guy, after some random time, will now be candidate and vote for me, okay? And then again it goes fine, okay. So here's, in timing, you have 3 followers, and the number is kind of the term, huh? So it starts, 0 millisecond. Each one of them has a random number for the timeout, okay? Stop me if I'm very confusing, huh? Yeah?
Can candidates vote, or is it not allowed to vote?
Yes, the candidate votes for itself.
But not for all,
No. The candidate will always vote for itself. yeah. They're not humans. Okay, so here after 150 milliseconds, 150 milliseconds, this guy wakes up first. It has the smallest number, huh? After it has the smallest timeout. These guys are still timing out, so it requests vote. This request vote message somehow fails because this is very harsh system, but that's okay. I get a vote and I have a majority. Yes, 2 out of 3. So I'm the leader. Now we go into this term 2. So the red L is the leader. Okay, but it's not always so nice. Here we have 4 nodes, 150 milliseconds. Both of these guys wake up. Oh, that's kind of nasty. They both request votes. They both get 2 votes. But then they request votes from the other guys. But this one already voted, and so did this one. So no votes. So they will not get any reply. Denied, no vote. So what happens? Well, they also ask each other, but that will be denied too. And then they sit and wait. But there's always a timeout, huh, during the election. So they will have randomized timeout. So one of those 2 guys will time out first. Of course, there's a small chance that they both time out exactly at the same time, and the same problem happens. But if you measure it probabilistically, that the expected time to elect will still be small. Okay, so this one now wakes up, requests vote, gets the vote, and it's the leader. It has a majority, 3 out of 4. Now, finally, this guy wakes up, says, hey, I want to be the leader, requests vote, but it's not getting the votes because they've already elected a leader. But eventually this one will send heartbeat saying, I'm the leader in term 3, and then this one will very nicely say, yes, you are the leader, and it will become a follower. Okay? So that's how the election works. So you see, you're using randomness, yeah?
So a Byzantine node can just set 100 and everybody will take
Sorry?
it. A Byzantine node can just set
Oh, a Byzantine node can really mess this thing up, yeah. But we're assuming no Byzantine nodes here, okay? No. This is not Byzantine algorithm, huh? Yeah. But this is supposed to be a very fast consensus algorithm running in trusted environment, huh? All algorithms don't have to be Byzantine, but yeah, you're right, it would not work in Byzantine, huh? So now we have log replication. So the leader manages the logs. The log is the data that's stored in the stable storage. So this basically is done using the quorum. So it starts with, the red ones are uncommitted. So the leader puts this one there, uncommitted, but it's not committed yet because it doesn't know that it's in a majority. Then it sends a message to the other 2 saying, please add Sally to your logs. So they all add Sally, but they don't know that it's stored in a majority, so they're still red. That means if they would crash, it would go away, okay? Okay. Now, when this one sends a message back saying, okay, this Sally is now committed, because I know that it exists in 2 disks, okay? I know that it exists in 2, and that's enough for it to be committed. Okay, because if a majority of the nodes stay up, then the the data will always be existing. And then this one says, okay, and then, but these two do not know yet that Sally exists in the majority. So the leader tells them, okay, now we're fine, now it's permanent, and they become blue everywhere. Okay, so blue basically means that the stable log exists in a majority of nodes. Okay, so using a quorum algorithm, it will not go away. Okay, that's the point. Okay, and here's another one, a next node information, heartbeat. Okay, now there's another, it does more work, and Bob was added, so it starts out being blue, okay. Appending, it's all blue, and once the message gets back, this one turns to, the red one turns to blue, because I know it exists in a majority, okay. Okay. Ah, it should have been here red. Bug in the slide, ooh. Okay, there should have been red bobs there. Wait. This slide has a problem. The values have become red again. Okay, forget that slide. Now these two become blue because they know that Bob exists in a majority. Okay? Yes? No, it's okay. You have the right to scratch your head. So here's application with more nodes. So Sally goes everywhere. Sally becomes blue. Then it becomes blue everywhere. Now there's a network partition. Oh, that's really nice, okay? The network breaks here. So the top guys can talk to each other and the bottom guys, but there's nothing can cross the red line. So what happens? Because the leader is on the top. Well, L1 does Bob, sends the Bob. It's okay, but it's still red. Because 2 is not the majority. So this one will wait for more, but it's waiting and nothing is happening, okay? Now, what happens? Just waits and waits. Eventually, these guys in the bottom, they also wait. And there's no more heartbeats. So they will time out and do another election. So this one becomes the candidate, okay? And it becomes a leader because it has a majority, which is 3, okay? Fine, so L2 is the leader in term 2. But L1 still thinks it's the leader in term 1, huh? Okay, but term 2 is higher than 1. So L2 does a Tom, and puts Tom in there, and Tom becomes blue here, because it's in a majority, which is 3, yeah? Okay, and then the 2 others also make their Toms blue, and now the network is repaired. There's no longer a partition. Ooh, what's going to happen between these 2 guys? Well, both of these think they're leaders, okay? Both of them. But the bottom 3, they know they're in a higher term. So L2 will send a message, and L1 gets a message from L2. And L1 says, ooh, this is a leader that's in a higher term than me. So L1 steps down. Real humans might not always do that, but this one will do that. And it becomes a follower. So L2 is the new leader, okay? And then the Tom is eventually copied to the other guys, okay? And the final thing is log compaction. The problem with the log is that it grows. Because the log, it's key value store. So in a particular key, I update. I put in the log. Later on, if I have a key, I keep track of operations. I update the same key, I put it in the log. So the log will eventually have all the updates, but maybe many updates for the same key. So it keeps growing. But you can get rid of most of those because only the last one is important, huh? So then it talks about log compaction. So there's techniques for log compaction, which I'm not going to talk about. So you make a snapshot, for example, you can either make a snapshot of the total database write it to memory and get rid of the previous log, or you can somehow keep only the last ones, the last updates. So there's different ways, but I won't go into that. So I think we're done. Okay, so that's Raft. So you see how it works, huh? So conceptually, it's straightforward, huh? You're electing, or the leader is running the show, and it's using a quorum to make sure that the log is consistent. Huh? It's always in a majority, and of course, the devil is in the details. There's still lots of little details on corner cases, but there is a paper which I will put in the Moodle, and if you're curious, it's easy to find also on the internet, huh? If you want to learn really how Raft works. But you have here the basic idea. Okay, so now we reach the end of the course. Question?
Can the followers not submit something to the log? Is it only the leader who decides what?
Only the leader. The followers also always obey the leader. So the followers, no, they will put something in the log, but it will be red thing, and only the leader can decide when it becomes blue. What is blue? What is actually, only the leader decides that. So if the leader is the one telling the followers to turn their log entry blue. Because I think so. Let's see. I think it can. I think they can all.
Because in all those examples, always the leader who first wrote something and then broadcasted it. But it's possible that one follower decides to, want this entry.
No, I don't think so. It's all going through the leader. Because it has to be consistent. Because you don't want to, the leader decides what is stored. Okay?
Yeah,
so a follower cannot decide by itself to store something.
Can it, I would like to store this in the log, so I propose to the leader.
You propose to the leader, and then the leader accepts that, yeah. It goes through the leader.
So you can still make propositions.
I think, yeah, because they can all run, huh? So it's a consensus algorithm, so basically they can all propose, but the leader decides.
Yeah.
The proposing is meaning sending message to the leader, and so it's an optimization, the leader is always the one making the decisions. Remember, in our consensus algorithms, we always had like a coordinator, rotating coordinator, and it was the one making the decision, in a sense. Whereas in Paxos, it's kind of very decentralized. But here, it's an optimization. There's always only one guy that decides. And the fact that that guy can crash is solved by doing re-elections. Okay? So only one decides. So that's how it's a consensus. They can all propose to Sally, but only the L can decide. It's a consensus algorithm, huh? Still, huh? So, but it's and anyone can propose, but the L is the one deciding. Okay. It's okay? If I'm telling bullshit, you have to tell me, yeah? But I think that's how it works. Yeah? Because it's a consensus. Okay, so we now reach the end of the course. Maybe I say 2 or 3 things about the exam, I don't know. So I'm almost done correcting the midterm. You will get the results by Friday. Okay? So the exam will be like the midterm, except more. And there will be one question corresponding to the midterm, but the others will be after. So it's both theory and practice. So anything that I show code of, I can ask you to make some variation of that code. Huh? Small variation. Huh? So for example, we did causal order broadcast. Maybe I ask you how to do FIFO broadcast, which is actually simpler than causal order because there's no transitivity. So for that, basically the sender and the receiver just have to keep track of sequence numbers. So it's all stuff that we saw. So I can ask you to write small bits of code like that, but also to make like theoretical definitions, of course. Huh? All the theory definitions, all the theory we saw, I can ask you. So I could ask you to do routing in a DHT, for example, and to explain how it works. and to explain how it converges to a single node with intervals that get smaller, for example. I can ask that. Or I can ask you to explain how to do, to estimate the number of nodes in a network using gossip. And explaining it the way I explained it in the course, using the techniques that you need to do to make it really work in practice. Okay. So basically, and it's all going to be on the slides. So anything that's not on the slides is not part of the course, but of course you can always read in the books and stuff if there's anything confusing. Yeah? But it's only stuff on the slides. And that's it. Okay, so we're at the end now, I think. So thank you very much. Thanks especially to my faithful followers who managed to stay here and listen to me for the whole quadrimester. So we're done, and I wish you good luck on the exam.